Welcome to the Deep Dive. Today, we're looking into one of those really fascinating areas of science, where sometimes the most abstract ideas, things that seem purely theoretical, actually end up reshaping our future. And we've got a perfect example today. We're diving into, a genuinely groundbreaking discovery about a really mysterious quantum particle. It's called a lone spinion.
That's right. And for this deep dive, we're mainly drawing on a fantastic new paper that just came out in Physical Review Letters. It's from researchers at the University of Warsaw and the University of British Columbia. And crucially, there's also experimental backup. Some really compelling confirmation published very recently in Nature Materials.
Okay, so what's the plan?
Right. Our mission today is basically to unpack this. What even is a spinion? Why is finding a lone one, just a single spinion, such a big deal? And, what does it all mean for how we understand magnetism and maybe even for the future of quantum tech?
Okay, sounds fascinating. To really get why this quantum stuff is so important, maybe we should start with the basics. Magnets. We all know magnets, right? But our history with them goes way back, like ancient times back.
Yeah.
People finding naturally magnetic rocks, magnetite. Can you imagine finding a rock that just pulls things? Must have seemed like magic.
Absolutely. Pure wonder.
And it wasn't just a curiosity, was it? That led to something huge.
Exactly. Fast forward a bit, and by the 11th century, inventors in China had figured out how to use this. They developed the first compasses.
Which completely changed navigation, exploration, everything.
It really did. Suddenly, you could navigate much more accurately over long distances, over oceans. It was revolutionary.
And now, magnets are just everywhere.
Completely ubiquitous.
Yeah.
Think about it. Data storage, like hard drives, loudspeakers, electric motors in, everything from EVs to washing machines, MRI scanners in hospitals.
Yeah, those incredibly powerful medical imaging machines.
And they're still vital, even saving lives.
And, let's be honest, holding up postcards on the fridge, too.
Right.
Yeah.
Linking the profound to the everyday travel souvenir.
But here's the kicker, right? We used them for centuries, millennia even. But we didn't really understand the fundamental why behind magnetism for a very long time.
That's the surprising part. It was a real puzzle. In fact, brilliant physicists like Niels Bohr and Hendrika Johanna van Leeuwen actually proved, mathematically, that you couldn't explain magnetism using classical physics, the physics of Newton, Maxwell.
It just didn't work.
So hang on, if classical physics failed, how did we finally crack it? What was the missing piece that explained, why my fridge magnet sticks?
Well, it wasn't magic, though it probably felt like it. The breakthrough, the real answer, came with quantum mechanics in the 1920s.
The quantum revolution.
Exactly. That's when we finally understood that magnetism, at its core, comes down to the interactions between electrons. Specifically, something called the spin of the electrons.
Okay, spin. That word always sounds a bit literal. Is the electron actually spinning? Hey, yeah, it's a bit of a misleading name. It's not spinning like a top. Spin is more like a fundamental intrinsic property of the electron, just like its mass or its electric charge. It's just there, part of what makes an electron an electron. And for electrons, it has this specific quantum value. We call it spin 12. It's a type of intrinsic angular momentum. And interestingly, this spin can point in basically any direction.
Okay, so quantum mechanics gives us electron spin, and that's key to magnetism. But you mentioned something even stranger earlier, this idea of electrons sort of splitting.
Right. That's where things get even more quantum and pretty weird. It started theoretically. Back in 1931, Hans Bethe came up with this incredibly elegant mathematical solution for a basic model of magnetism. It's called the one-dimensional Heisenberg model.
Like a chain of tiny interacting quantum magnets.
Pretty much, yeah. A simplified but fundamental way to study magnetism. Bethe's solution was a huge step.
But the splitting idea came later.
Much later. Jump to 1981. Ludwig Fedave and Leon Tokdejan were looking closely at Bethe's solutions, and they realized something astonishing. It looked like the fundamental way you could excite this magnetic chain wasn't just flipping one electron's spin. Normally, flipping a spin changes the total spin of the system by one whole unit, right? But their work showed that the real fundamental excitations, the building blocks of magnetic excitement, so to speak, actually changed the total spin by only half a unit.
Half, not a whole electron flip.
Exactly, half. It was like the electron spin excitation had somehow split into two pieces. And these exotic half-unit excitations got a name. Spinons.
Spinions, okay. And experiments eventually found these.
They did. Experiments confirmed that spinons exist. But there was always a catch. They always appeared in pairs, never just one spinon on its own.
Ah, so the theory suggested these half-unit things were fundamental, but experiments only ever saw them glued together in pairs, made them seem a bit less fundamental, maybe.
Sort of, yeah. Or at least it meant our understanding was incomplete. Why always pairs? If they're fundamental, shouldn't we be able to see just one? That was the lingering question.
Until now. So how did this new research, the paper in Physical Review Letters, finally crack it? How did they manage to isolate just one?
This is the really cool part. The team from Warsaw and UBC figured out a surprisingly simple way, theoretically. They showed that you can create a single lone spinion. How? Just by adding one extra spin to the ground state, the lowest energy state of that same one-dimensional Heisenberg model we talked about. It's an incredibly elegant theoretical insight.
Wow. Just add one extra spin and suddenly a lone spinion pops out.
Essentially, yes. It satisfies the conditions needed for a single spin 12 excitation to exist stably on its own.
And I heard they found another way, too, using a different kind of model.
That's right. They showed the same thing happens in a slightly simpler, perhaps more intuitive model called the valence bond solid, or VBS.
Okay, VBS. What's that like?
Imagine like a chain where each electron spin is perfectly paired up with its neighbor, like little partners holding hands all down the line, very ordered.
Okay, nice. Neat pairs.
Exactly. And in that VBS model, a lone spinion is basically like creating one single electron that doesn't have a partner. It's an unpaired spin. And this lone defect, this unpaired spin, can then travel along the chain, moving through the network of pairs.
So, like one person cutting in on the dance floor and moving solo through all the couples.
That's a great analogy. Yes, exactly like that. A single, unpaired entity moving through an ordered background.
And the most exciting part, this isn't just theory anymore.
Precisely. This is where the Nature Materials paper comes in. Researchers, Zhao and colleagues, performed experiments that actually observed this. They confirmed the theoretical prediction. They managed to create and detect these lone spinions in a real material.
That's huge. So theory predicted it, and now experiment has seen it. Wow.
It really is a big deal. So what does this all mean for you listening in?
Well, first, it's a major step forward in just fundamentally understanding magnetism at the quantum level. It opens doors to finding other, new, weird quantum magnetic effects. And the key thing here is why spinions happen. They are a direct result of really strong interactions between electrons combined with purely quantum effects, especially quantum entanglement.
Ah, entanglement. The spooky action at a distance, as Einstein wasn't too fond of calling it, where particles are linked no matter how far apart.
That's the one. This deep quantum connection allows these strange fractional things like spinions to even exist. It's the interactions and the entanglement working together.
And this kind of mechanism, strong interactions leading to weird emergent particles, it's not just in these magnetic chains, is it?
No, not at all. Similar physics, this idea of strong interactions and quantum effects creating exotic behaviors, is thought to be crucial in other massive areas of physics. Think high-temperature superconductivity.
Wow, materials that conduct electricity with zero resistance, potentially revolutionizing energy. Exactly. Or things like the fractional quantum Hall effect, which happens in ultra-thin, two-dimensional materials under strong magnetic fields. These are really fundamental, complex phenomena, and understanding things like spinions helps us chip away at them.
And you mentioned entanglement is key.
Yes, and entanglement isn't just some weird theoretical curiosity anymore. It's the absolute bedrock of quantum computing.
Right, the whole basis for potentially incredibly powerful new kinds of computers.
Precisely. So understanding phenomena like spinions, which are born from entanglement, gets us closer to understanding, and maybe even controlling, the very processes needed for quantum computation.
It really ties together, as Professor Christoph Wolfeld from Warsaw said, and it puts it nicely. Our research not only deepens our knowledge of magnets, but can also have far-reaching consequences in other areas of physics and technology.
It's a perfect summary.
It really is amazing, isn't it? How something that sounds so abstract, alone spinning, a fraction of an electron's spin wandering about, connects so deeply to how reality works at its most fundamental level, and how it could genuinely impact future technology. Makes you wonder what other weird quantum bits and pieces are hiding, waiting for us to find them on their own.
Absolutely. And that leaves us with a really thought-provoking question, doesn't it? Now that we understand how to find and study these single lone excitations like spinions, Where might that lead? Could it unlock breakthroughs we can't even imagine right now? Maybe in energy, maybe in computation, maybe something else entirely. What other lone rangers of the quantum world are out there waiting to be discovered, and what completely new scientific doors might they open up?